Hello everyone, welcome to my YouTube channel Versatile.
Now for the component which are subjected to complete liver stress, as we have discussed in the last lecture, for the component subjected to reverse stress, value of sigma m is equal to 0. That means mean stress is 0, and we have to design this component for infinite life and finite life. So let's begin with the design of component subjected to infinite life. Now, as we have discussed earlier also, the 10 raised to 6 cycles, that is log to the base 10 raised to 6 is 6 on log paper. This 10 raised to 6 cycle is defining criteria for finite life and infinite life. So any component which completes more than 10 raised to 6 cycles and then fails, that component has completed an infinite life. That's what we are saying. So we have to design the component subjected to completely reverse stress for infinite life, right? Now for infinite life, the criteria of design is SE. Hence, the value of stress equations are if it is a direct stress, that direct stress means if any component is subjected to sigma T, if any component is subjected to sigma C, bending stress, bearing pressure, these are all direct stresses, means which are indicated by sigma. So if any component is subjected to these stresses, the value of stress calculated by endurance strength divided by factor of safety. And if any component is subjected to shear stress, that is either torsional shear stress or direct shear stress, that stress is calculated by SSE upon factor of safety. So, SSE is 0.5 times of SE always in case of endurance strength. So this is the equation for stresses for components subjected to completely reverse stress for infinite life. As we have discussed, sigma is direct stress amplitude and shear tau A is shear stress amplitude, and NF is a factor of safety. As mean stress is 0, we are only finding out stress amplitude for direct stress and stress amplitude for shear stress. Now, for the components subjected to completely reverse stress and for finite life, what will be the equations that we have to discuss? Now, as any component which completes less than 10 raised to 6 cycle before failure, the life of that component is called as finite life. So, in between 10 raised to 3 cycle to 10 raised to 6 cycles, the component which fails is called as a component completing finite life, and if component completes more than 10 raised to 6 cycles, that component is called as completed an infinite life, right? So, for the component subjected to completely reverse stress and for finite life, uh, the design is based on a fatigue strength whose value can be founded out by an SM diagram. Now, if you see for an infinite life, the strength of the component is constant after an 10 to 6 cycles, and that strength is called as an AC. But in case of finite life, the strength is varies in between 10 to 3 to 10 to 6 cycles. So this varied strength is called as a fatigue strength, right? And that fatigue strength is called calculated from the ascent diagram from 10 to 3 to 10 to 6 cycles. So how that fatigue strength is founded out, that we have to discuss in next slide. So if you see this diagram is the representation of the same diagram which we have discussed earlier. Only we are taking the part from SN diagram only for 10 raised to 3 to 10 raised to 6 cycle for the component subjected to finite life. Now, if you see from 10 raised to 3 to 10 raised to 6 cycles, the slope of the SN diagram is indicated in this diagram. So the starting point on the strength is from 0.9 times of SUT, and from 10 raised to 6 cycles, or at the point of 10 raised to 6 cycles, the strength becomes horizontal, and that is called as AC. So these are the two defining criteria of the strength and the number of stress cycles beginning at 10 raised to 3 cycles to 10 raised to 6 cycles. So area below this particular line is the safe region, for design of components subjected to completely reverse stress for finite life. Now the design which we have to do in this case is we have to find out two parameters. That is, either we have to find out how many number of stress cycle that a component has completed before failure, that is n, or how much is the maximum value of the strength that component has reached before failure, so that is fatigue strength. And for finding out these SF or number of stress cycle, we are going to use an equal angle triangle method. So in that case, in that equal angle triangle method, let's consider that uh, we have to find out the unknown number of stress cycle and fatigue strength. So we take equal angle triangle method. So let's assume that we have to find out the fatigue strength at this point or number of stress cycle at this point. So we take a horizontal line from this point which cuts an y-axis, and we'll take an intercept of this point on the x-axis. So at that point, the number of stress cycle are logged to the base 10 n, and on the y-axis, the intercept is logged to the base 10 sf. So find out any one unknown value of from this SN diagram, either strength or number of stress cycle. We take equal angle triangle method. So what is that equal angle triangle method? So if you discuss this formula, the numerator and denominator on the left side and numerator and denominator on the right side are from the equal angle triangle method. So for this big triangle, if I change the color of my pen and if I show you this, for this big triangle like this, let's assume this is triangle 1, and for this small triangle, let me again change the color. For this small triangle, let's assume this is triangle 2. So in this case, for a big triangle, on y-axis, the difference of these 2 points, that is log to the base 10.9 times of SUT minus log to the base 10.9 of AC. In the denominator, for this big triangle, the two defining parameters are log to the base 10 raised to 6, that is 6, minus log to the base 10 raised to 3, that is 3, is equal to, for the small triangle, on y-axis the defining points are log to the base 10.9 times of SUT minus log to the base 10 SF. So in the denominator, the two defining points are log to the base 10 n minus log to the base 10 raised to 3, right? So from this equation, all these parameter 0.9 SUT, AC, 0.9 SUT, 6, 3 and 3 are known. So only unknown parameters would be SF or N. So any one parameters would be known, and we have to find out another parameter. So this is the way we have to design the component subjected to completely reverse stress for finite life. And if a fatigue strength is known, we can find out the stress amplitude, that by equation SF upon NF, and stress amplitude for shear stress, that is SSF upon NF. Again, SSF is equal to 0.5 times of SF, right? So while discussing the problem, we'll analyze how this diagram is used for solving the problem in case of completely reverse stress for finite life. So we'll take one problem for component subjected to infinite life and one problem for component subjected to finite life. Now let's discuss this problem, and we'll analyze the different conditions for designing the component. Now in this case, there is a plate which is subjected to a completely reversed force of, if you see, the completely reversed force is shown, there is a plus minus value, and the plate is made up of a material of 20C8 having SUT 440 megapascal, and the different factors which are used for these plates are KT stands for theoretical stress concentration factor, Q stands for North sensitivity, Ka stands for size factor, Kb stands for shear stress factor, then Kg stands for reliability factor. The plate thickness is 30 mm. That means if you draw 3D diagram, then this thickness is equal to 30 mm. right? If the required factor of safety is to determine the maximum completely reversed axial force, that means this axial force, maximum completely reversed axial force, the problem itself suggests that this component is subjected to completely reversed axial force, right? And we have to design this component for infinite life. So component subjected to completely reverse stress for infinite life. This is the case of the problem. Now, as we have discussed, this particular plate will be subjected to tensile stress, and as this is a completely reverse stress, we have to find out tensile stress amplitude only, because mean stress is 0 for completely reverse stress, and this tensile stress amplitude will be given by AC upon NF, because whenever component is subjected to infinite life, the criteria of design is AC. Hence, stress is strength upon factor of safety. So, strength is endurance strength. So, the aim of this problem is to find out F. Now, if we get AC upon NF, we will have an tensile stress amplitude for this particular diagram, and by using that tensile stress amplitude, we can find out, we always know that tensile stress is equal to force upon cross sectional area. Now, what is the cross sectional area for this diagram? So if you take cross section at the point of an discontinuity, the cross section will be like this, right? So we have to take the cross section where the material removal takes place. So if I draw this diagram here, in this view, so at the center there is a hole of diameter 25 mm. So this diameter is 25, so this is equal to 25, understand? And only material removal or cutting of the material takes place at this portion. So we have to take cross section like this. This is 30 mm and this complete diameter is 50 mm. So what cross section we have to take is the cross section will be 50 minus 25, that is 25 minus 30, right? So this is cross sectional area. The force we have to find out, so this force plus minus we have to find out, and if tensile stress will be calculated from this equation. So the amplitude, first we have to find out AC. Now AC will be equal to AC dash multiply by all modifying factors from Ka to Kg, right? So from this factor, whichever factor is unknown, we have to consider that as 1. Now AC dash is always, we know that if SUT is less than 1400 megapascal, we have to take it as 0.5 times of SUT. So how much is SUT? 440 megapascal. Hence 0.5 times of 440 megapascal is 220 into Ka is equal to 0.67. So let me correct this. So it is 0.67 from this diagram, from the given data in the problem. Then Kb is 0.85, right? Then Kc is unknown, that's why it is equal to 1. Kd is unknown. Ke is equal to 1 upon Kf. Now why it is written as Kf? Whether Kf is known or unknown, it is unknown, but in the problem Kt is given and Q is given, and Kf is related to Kt and Q, hence Kf is written as is equal to Q into Kt minus 1 plus 1. So by putting Q into K and Kt, we can find out Kf, and Kg is 0.897, which was given in the problem. Hence, after putting all these value, the value of AC that we get from this equation is 51.08 megapascal. So you have to calculate on your calculators, and you have to cross check whether this AC is the answer is coming 51 megapascal or not. This AC we have to put in the equation of tensile stress amplitude AC upon NF. So that AC upon NF will give us tensile stress amplitude. Now that let's put this AC here, and tensile stress amplitude will be given as 51.08 upon NF, where NF is equal to 2 Hence, the answer of tensile stress amplitude that comes as 25.54 megapascal, right? This is tensile stress amplitude. This tensile stress amplitude is also equal to force upon cross-sectional area. Now, force upon cross-sectional area is 25 minus 30, right? So, tensile stress amplitude is 25 into 30. So, cross-sectional area is 50 minus 25 into 30. So, if we put 25 into 30, and only unknown value is the force, that plus minus force is equal to, so 25 into 30 multiplied by 25.54 is 19.55 kilonewton, right? So the answer for unknown completely reversed force is 19.55 kilonewton, right? So this is the way we have to solve the problem for components subjected to infinite life.
Don't forget to like, share, and subscribe my YouTube channel. Thank you. Thank you very much.